Right, hi, it's Mr. T here. I'm going over the third and last question of the Level 3 Mechanics 2016 NCA paper. This question is on simple harmonic motion, so let's start on this now. So let's read through the question. What we've got here is a bumblebee hanging off a spring. Tom pulls bumblebee down 10 centimeters. That's going to be our amplitude. And actually, if I put it in meters right now, well, I remember 0.1 meters. Moves in simple harmonic motion. That's good because we know we're going to use all the tools that we use for simple harmonic motion. Two conditions necessary for simple harmonic motion. Well, the first one is that the force, we'll call this the restoring force, is proportional to the displacement okay, and the other bit is it restoring force always acts in the opposite direction, or restoring always acts towards the equilibrium. Sorry, towards the equilibrium point. Now you could also say that if I wanted to do this using an equation, I could just say that F is proportional to negative y. Okay, so it's force acts in the opposite direction to the displacement, but it's proportional to it. Right, so the bumblebee has an oscillation period of 1.57 seconds. That's our time. Okay, we need to calculate here the acceleration, and they've given us the time. So what we need to do is, it says it's from the lowest point, so this is the maximum, so I'm going to use the first line of equations. So acceleration equals negative amplitude omega squared cos omega t, right? So I know the amplitude, it's 0.1 meters. I don't know the time, I know the acceleration, so I'm going to have to rearrange this equation. But I need to find out omega first. And what I know is that omega equals 2 pi f. So angular frequency is radians per second. So I also know that t equals 1 over f. Yeah, so once I put these equations together, I substitute them. Well, I don't have to put them together. What I can do is I can solve this one first. This is possibly the easiest way to do this. So frequency equals 1 over time period. Let's do that. Frequency equals 1 over 1.57. Just let me do this on my calculator. Is 1 divided 1.57. 0.637. Okay, and then what I can do is I can go, well, omega equals 2 pi times whatever that answer was I just got, 0.637. Okay, so multiply by 2 and multiply by pi equals 4.00. So angular frequency 4.00 radians per second. Negative 1. Okay, so that's cool. We can we've got all the values I need to put into my equation now. But first, let's rearrange the equation. So what we've essentially got here is we've got these values that we are cosigning. So what we want to remove is the values at the start that are multiplied to cosine. So they're multiplied on this side, so we're going to take them to the other side and put them under A. So we get A negative alpha omega squared equals cos WT. Okay, and the only way to move a cos to the other side, a cosine to the other side, is to give it the inverse of a cosine. So basically, WT equals cos negative 1 of everything else that's here, which is acceleration, negative A omega. And then if we go down, do one more step of rearranging this equation, I get that I move cos for negative A omega divided by omega. Okay, so this looks kind of complicated, but basically if we just do it all sequentially, it'll all work out perfectly fine. So we have cos, whatever the answer is to this bracket, which is acceleration. What do they tell us for acceleration? Oh my goodness. Okay, so we're just going to go about and calculate the acceleration. So acceleration equals negative, we said the amplitude was 0.1 meters times omega squared, which is 4.0 per second negative 1 squared. Let me just put the rest of this down here, times the cosine of 4.00 meters second negative 1 times 0.25 seconds. So I put this in my calculator. Look, when I carry out these types of things in my calculator, because it's quite a lot of numbers going into once, if you have the time, you might just sort of simplify each part before doing the final calculation. So I'm going to simplify this brackets. 4 times 4 is 16. 0 meters squared second negative 2. And I'm going to simplify this cos. So I've got 0.4 times 4 times 0.25, that's 1. So I'm going to do cosine of 1 equals wait a minute, I need to make sure that I have my calculator in. Okay, so we're going to do this times the cosine of 1 times cosine of 1. Okay, so that's 4 times 0.05, and this gives us a grand total of 0.864 meters second negative 2. That's my acceleration. Okay, so let's go look at the next question. Tom pushes the toy bumblebee with very small force at regular intervals of time periodically. So eventually it's moving up and down with a very large amplitude. State the name of this phenomenon. Explain the bumblebee's motion develops a very large amplitude. Okay, so this is called resonance. Okay. And this happens because resonance occurs because a driving force, we call it, okay, so a driving force is applied at a regular interval, or sorry, let's say at the natural frequency. So the natural frequency is the frequency the bumblebee will oscillate. And remember, that was 1 over the time period. So it gets a very large amplitude because the amount of energy, so I guess you could say the amount of energy you're supplying is bigger than the amount of energy lost from friction. Is larger than that lost by friction. Than that lost by friction. Okay, and now we're into the last question. And Tom stops pushing the bumblebee. This displacement is at 20 centimeters. Use axes below to draw a graph of displacement against time for 3 complete oscillations. Okay, so I'm just going to look at the scale here. I think I'm going to do 1 complete oscillation to there, then 2, then 3. Okay, so starting from y is at plus 20. So I'm just going to put some values in here that I'm going to use to help me when I draw my graph. So this is its maximum here, okay, and the maximum down here is, so here it's going to go through the middle. Sorry, no, it's not. Here is going to be the maximum on this side, okay, and then here it'll go straight through the middle, and here it'll go through the middle, and up here it's at the maximum again, but the maximum is less each time. Now the reason the maximum is less each time is because it's losing kinetic energy, okay? So there, 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 there. Okay, so the other thing I need to do is, this is 1 complete oscillation here, so I need to put the time period in here. The time period was 1.57 seconds. Here, right? Or I could call that t, and the time period here must be double that. 3.14 seconds. So let's just sketch the graph in here. Okay, here we go. This is going to be tricky for me with this pen. Okay, so pretty much down through here, down to the bottom, through the center, to the top. Now, one of the most important things here is that we see that it's getting smaller each time, the amplitude, because it's getting less and less. That's getting less and less energy, so the displacement is less and less each time. So I just got to roughly draw this. I mean, it's pretty scratchy. And then I'm going to actually, look, I've put the times in the wrong place, so I'm just going to cross these out. And I'm going to write them here. 1.57 seconds. And, oh no, it wasn't in the wrong place. Let's go back to doing that again. 1.57 seconds. And there we go. That's the end of the paper. I have a funny feeling I have missed this bit here. Let's just do that through there, just to make sure that I go back to the start again. So that's 1, 2, 3 complete oscillations. Okay, thanks for watching these videos. I hope that they have helped.